Let's get started. Let me get the pointer out. So today I'm going to talk to you guys about what controls river water chemistry. And one of the first things that comes to mind when we study river is a very philosophical quote that no man walks into the same river twice, because he's not the same man, it's passage of time, and it's not the same river. So what it conveys is that the river is in one part flowing in a unidirectional way when it's coming off the mountains and going through the plains. But as soon as you get to the estuaries, a river is tidal. It goes forward and backwards with high tide and low tide. However, if you sit at one single point, you will never find the river chemistry to be the same over days and days and months. So the situation is very dynamic. And what we are attempting to do is to study how these processes which are happening inside the river, how they modulate river water chemistry, and in turn the flux of material that goes from the continents to the ocean. Now, this work has been done by a large group of people, mainly by Pratyusha, who is my PhD student. She is about to finish up. And a lot of other people have helped us through the process. Satya was part of a lot of field work where he's holding up a Niskin bottle with which we would sample the rivers. This is a large group of people from IIT Kharagpur who were pivotal in terms of the flux measurements and water flux measurements through ADCP studies. And here you can see on a morning when we are going out for the cruise, how the PhD student reacts to the supervisor giving her some instructions. Now, why do we study river chemistry? One answer is that you can take a boat and roam around very pretty sites, but that is not the case. That's not why we study river chemistry. We study river chemistry because rivers are a conduit of material from the continents to the ocean. And if you look at the total amount of material being delivered by rivers to the ocean, global average, we are looking at trillions of moles per year. And the numbers are dominated in the anion space by bicarbonate ion and in the cation space by calcium ion. So we are supplying 1 trillion mole of material to the oceans per year by all global rivers, and also around 10 trillion kilograms of sediment per year, of which this is a snapshot of the Ganga Brahmaputra system. You can see the main channel of Ganga coming in and the main channel of Brahmaputra river coming in. This is the Bengal basin. And you can see from a satellite image how much sediment is being poured into Bay of Bengal. So in terms of total sediment discharge, these two rivers combined account for around 26% of the global flux. So we are actually looking at 2.5 trillion kilograms of sediment being discharged in the Bay of Bengal in this photograph. So the question is, what controls river chemistry? In the mountains, above the floodplains, it's the chemical weathering of rock that controls river chemistry. It's the starting point. It supplies material to the river, dissolve ions to the rivers, because we know rainwater is like distilled water. And weathering is nothing but carbon dioxide reacting with water to form carbonic acid and reacting with minerals to have some part of the mineral being dissolved and supplied to river, and some part remains behind, what we call primary clays. But once we move from rivers to estuaries, multiple processes kick in. So this is a schematic diagram of what happens in an estuary. We are at the freshwater end member. We are moving to some saline water end member, and on the right-hand side is open ocean seawater. So salinity around 0.1, salinity around 31. So in between, all these processes take place. What are the major processes? There can be precipitation or dissolution of mineral phases. A classical mineral phase which is precipitated out is manganese oxyhydroxides. Now, keep in mind, all rivers carry a lot of organic matter with it. There is a lot of biological productivity there because there is a lot of nutrient there. And that's why rivers are important on a global scale, because they supply a lot of bioessential nutrients to the coastal ocean. They can be nitrate, phosphate, they can be iron, zinc, what we call the micronutrients, the trace metal-based micronutrients. Now, the organic matter which has been carried by the rivers can undergo oxidation. And we know when we oxidize organic matter, we produce carbon dioxide. And when we produce carbon dioxide, we lower the pH. There can be anthropogenic input. There can be ion exchange between the suspended particulate matter, what we would call SPM in this lecture, and seawater. And there can be benthic boundary flux. We can have material coming into the river as groundwater discharge, and so forth and so on. So how does all these processes control river chemistry? If you take a cross-section of the river, this is what you will observe. You have the organic matter in the river water, which is being oxidized by bacteria. You have these suspended particulate matters, which can have certain elements attached to it. Here is an example of barium. Barium is usually attached to surface suspended particulate matter in fresh water. But as soon as you hit the seawater, there is a lot of sodium ion in it. So the sodium will push the barium out. Whereas some suspended particulate matter can have a calcium carbonate shell around itself. It's just biogenic calcium carbonate precipitation. And when the pH drops, this calcium carbonate can dissolve. So there are multiple processes as a whole which can control river chemistry. Now, what we're going to look at is how these processes can be deciphered from river chemistry analysis. So the research questions that we are interested in this particular study was how fluid particle interaction changes estuarine concentration of elements. Is there a significant groundwater contribution to rivers? And normally, when we calculate flux of metals from rivers to ocean, what we do is we measure the concentration of these metals in a freshwater end member. We have a total river flux, we multiply the two, and we now have a metal flux from a particular river to the ocean. Now, what I'm going to demonstrate in this lecture, that is a wrong method. Because when river water passes through an estuary, the effective concentration of a metal in the water system can either go up or go down based on the processes that they participate in. So simply taking a freshwater concentration and multiply it by total flux doesn't give you a total flux of a particular metal going into the ocean by a particular river. Okay. We have already discussed about this, that rivers carry 1 trillion moles of material from the continents to the ocean. And of these elements, calcium, magnesium, potassium are the major ones, including sodium, that we are interested in. But more than these major elements, there is a flux of iron, zinc, transition metals at a very low concentration, which can sustain primary productivity in the coastal ocean. So what is the difference between river water chemistry and seawater chemistry? Now, seawater is dominated by particular kinds of ions present in it. Of a kilogram of seawater, around 34.4 grams are dissolved ions. And within which dissolved ions, we see that chlorine dominates. Sodium is the biggest cation. The next biggest one is sulfate, followed by magnesium, then comes calcium, potassium, bicarbonate, and other ions. And among these others sit all the transition metals, which are bioessential micronutrients. So river water chemistry dominated by bicarbonate and calcium ion. Seawater chemistry is dominated by chlorine and sodium ion. So mixing of these two end members can be easily deciphered because the major ion concentrations are significantly different. So we'll start with these basic background knowledge. Now, we have already talked about that there is around 10 trillion kilogram of sediment being discharged by rivers to the ocean. Let's look at what happens to these sediments when they cross the estuary. Now, this graph moves from left to the right. You're looking at river water through estuarine water to seawater. And what we're going to define river water as is any water which is below 0.2 salinity. The mid-salinity zone is the most interacting zone when you have fresh water coming in and interacting with seawater. And then there is the high salinity zone, which becomes kind of predictable in its behavior. So we have suspended particulate matter, we have dissolved metals, and we have organic matter in the system. Now, in the mid-salinity zone, we can have two different kinds of reactions going on. We can have desorption of these metals from suspended particulate matter. Some other metal can get absorbed onto these suspended particulate matters. We can have orthogenic formation of iron manganese oxyhydroxides, because we know river waters have a lot of iron in it, but seawater has close to no iron in it. Concentration of iron in river water is in high micromoles per liter. Concentration of iron in seawater is in very low nanomoles per liter. And once we move into the marginal setting, there is a change in EH and pH, which can lead to further precipitation of metals onto these iron manganese oxyhydroxides. Now, among the large rivers, so this is a global overview of large rivers, and the width of this line gives you an idea of how big the river is. We all know about the Amazon, the Mississippi, the Congo, Ganga, Brahmaputra system, Indus River. And this is the Mackenzie River, we have Mekong, we have Yangtze, and so forth and so on. So we're going to focus on this particular part of the world, looking at the Ganga-Brahmaputra system. And we're going to try and understand what are the major processes that are happening in the Ganga-Brahmaputra system. Now, the first question becomes, why the Ganga-Brahmaputra system? Is it because it's convenient for me to sample the Ganga-Brahmaputra system? No, there is a bit more nuanced approach to it. Now, this is an overview of the Indian subcontinent. We have the Indus River on this end. This part is the Pakistan part. This is India. This is Bangladesh. And we have Myanmar on this side. So you can see that the topography of the Indian subcontinent has a lot of feature to it. However, as soon as you get into the floodplains of the Ganga-Brahmaputra, it's nothing but flat. So there's a lot of weathering going on in this regime. So outside of the Ganga-Brahmaputra system, you have a topographic area, but Ganga-Brahmaputra system is a flat area, which has a huge implication. The huge implication is that in the floodplains, it's very difficult to create a dam. So among the rivers which are draining into the Bay of Bengal, Ganga-Brahmaputra carries around 1,037 kilometer cube per year of water, whereas all other rivers combined is almost 20% of the total Ganga-Brahmaputra discharge. So Ganga-Brahmaputra system dominates the discharge of Indian rivers on the eastern coast. Okay. And we already talked about the amount of sediment being carried by this river, which is around 26% of the global discharge. Now, in terms of water discharge, Ganga-Brahmaputra is around 4 to 5%. But in terms of sediment discharge, it's around 25%. And this particular diagram gives you an overview of how much sediment is being transported per continent to the ocean. And as you can see, the continent of Asia dominates with its sediment discharge. It's simply because of the fact that we have the Himalayas. Then you can argue that in the South America, we have the Andes. Why doesn't South America have such a large sediment discharge as the Asian subcontinent, for two particular regions? The reason is that the Himalayas sit in a monsoon setting where you have 8 years of the year, which is very dry, and 8 months of the year, which is very dry, and 4 months of the year, which has a huge amount of rainfall. So this oscillation between dry, sometimes hot, sometimes cold climate to a highly monsoonal climate allows for a lot of physical breakdown of material, which leads to a very large flux of sediments down the Himalayan rivers, whether that be Ganga, Brahmaputra, Mekong, Irrawaddy. All of these rivers are can be categorized as high sediment-bearing rivers. One of the biological evidence towards this is that the Irrawaddy dolphin. The Irrawaddy dolphin is practically blind because there is so much sediment in Irrawaddy river. Having for an animal to have an eye doesn't make much of a difference. So we have a large sediment discharge in these rivers. And if you look at the changes in sediment discharge before human intervention and after human intervention, the top plot gives you an idea of what used to be the sediment discharge before human intervention, and the bottom plot gives you a flux of sediment discharge after human intervention. One of the key features is that if you look at Amazon, before human intervention, we had around 400 metric tons of sediment being discharged to the Atlantic Ocean. However, with human interference, it has been brought down to 100 to 25 metric tons per year because of the creation of these dams. But once we move to the major Himalayan rivers, except for Indus, the other rivers have not suffered much in terms of sediment discharge, because in the floodplains, it is quite impossible to construct dams. So which is again visible in terms of sediment discharge before human activity to after human activity. There has been only 10% drop in the process. However, if you go to Guangzhou, the Yellow River, you can see the sediment discharge has dropped by 90% because of large amount of anthropogenic activity. So this is a system, Ganga Brahmaputra is a system which has a large fluid rock ratio. We have a large amount of sediment being transported. So any process which kind of encapsulates absorption, desorption onto sediment surfaces, precipitation, or overgrowth of other minerals on a sediment surface will be strongly manifested in the Ganga Brahmaputra system. Last but not the least is the anthropogenic influence. This is a population map of the Indian subcontinent. One of the key features is that outside of Mumbai or Bombay, on the west coast, Bangalore, where I'm sitting at over here, excuse me, most of the population of the subcontinent is kind of squeezed into this Ganga Brahmaputra floodplain. And you can see the Gangetic floodplain, if you include India and Bangladesh, kind of support fertile lands on the planet. And luckily for us, right at the edge of this Ganga Brahmaputra, extremely urbanized locality, we have these reserve forests which provides us with a unique environment to study natural processes as well as anthropogenic impact on these natural processes. We had already talked about this. We have a river which is carrying around 4% of global discharge in terms of water and 26% of sediment discharge globally. Now, this sediment undergoes a large change while it's being transported through the estuary. You don't need to chemically analyze it. What I have here is a picture of the sediment being collected at the lowest salinity, salinity 0.2, medium salinity 2, and high salinity 16. And you can see the difference in color of these sediments. And the difference in color is coming because they are undergoing chemical alteration. Certain elements are being lost and certain elements have been added to these sediments. We have given you an overview that there can be some absorption, some desorption, and orthogenic precipitation of iron, manganese, oxyhydroxide phases. Okay. Now, all of this got culminated with Tarun Dalai's work, which came out in 2018 in Geochemica Cosmochemica Acta. Tarun was looking at concentration of coppers in the Ganga estuary. And we have the city of Calcutta up here, and we are going south towards Bay of Bengal. And these are the locations along which the river was sampled. And so this is the edge of industrialized Bengal, and beyond which we don't have heavy industry in Bengal. So copper concentration around Calcutta in the river is around 26 nanomoles per liter. But once we start getting into the estuary, the copper concentration goes up to 107 nanomoles per liter, and it can go up to 178 and some point 190 nanomoles per liter. So with increasing salinity, we are observing an increase in copper concentration in the river. However, that's not possible because seawater contains very little amount of copper. And we had talked about it. This is a classical example of certain elements getting desorbed from the sediment into the fluid phase as the salinity increases. So our focus will be on the Ganga Brahmaputra system, and we're going to focus on the Bengal Basin. The lower part of the Bengal Basin, where the river undergoes a tidal process with a large residence time. So this were the sampling sites over which we worked. The city of Calcutta is sitting over here. We have sampled from above Calcutta all the way down to Bay of Bengal the tip of Bay of Bengal. Sampling was done for 2 different seasons, monsoon and non-monsoon. We have to be careful when dealing with a river which has a large difference in water flux based on the season over which you're sampling. Remember, 90 to 95% of the water flux happens during monsoon season and not during non-monsoon season. Now, one of the key features is that the suspended particulate matter load in the river. What we observe that as salinity increases, we should have a decrease in suspended particulate matter load. Keep in mind the SPM values are plotted in logarithmic scale, which means that each point on the axis is 10 times above the other point. The monsoon values are given in blue, the non-monsoon values are given in red. The dark blue versus the light blue is just different seasons of sampling, different years of sampling. Sorry about that. Now, what we observe that in the mid salinity region, between 0 to 3, there is a peak in suspended particulate matter load, after which it slowly tapers away. And obviously, the monsoonal SPM loads are drastically higher than the non-monsoonal SPM load. We can have loads up to few grams of material per liter of water in the monsoon season, which is huge in terms of SPM values goes. So how do we sample the river? We get on a boat, we go to these remote locations. The widest part of the river that we sampled was 8 kilometers wide, and the narrowest part of the river we sampled was around 2 kilometers wide. So this is a pretty large river. We use these Niskin bottles, metal-free Niskin bottles, to sample the river, and they're horizontal Niskin bottles so that there is no sediment sorting while they're being captured by the bottle. We measure water flux using an ADCP. This is a Doppler-based instrument. All of the physical parameters are measured on the boat so that each water sample is well characterized. And then the water samples are filtered through these custom-made filtering units, which are metal-free and which uses Teflon filtration. And then all the filtered water are kind of categorized, which will be analyzed later. In addition to collecting river water, we also collect sediment cores, and collecting these sediment cores are a logistical channel. Remember, I showed you that there is a reserve forest at the edge of the estuary, and we are at that reserve forest when we are collecting these sediment cores. This is Pratyusha and Orbi collecting the sediment cores, and the boat, there's no dock, so the boat has to be in the river. You jump off, then you crawl through the mud, and then you put your sediment cores in, and then you finally have a sediment core out. Keep in mind, these places are frequented by crocodiles, so it's not an easy task to do. And once the cores are collected, then you collect the pore waters outside of from the cores by using rhizome samplers, and you put a negative pressure, and these have a filtration unit at the tip of it. So the interstitial water within the mud is being collected by it. And this is one particular core that I'm showing you. You can see the yellow coloration is starting to develop. This yellow coloration is coming from precipitation of iron. As the anoxic water is being introduced to atmosphere and oxygen is diffusing inside. So these systems are highly anoxic. So there's a lot of redox active processes going on. And this is a classical example of how much work needs to be done. All these water being filtered through positive pressure, no usage of vacuum pump, just to ensure that we have great metal data. Now, coming to the results. Between monsoon and non-monsoon, this is how the salinity profile looks like. What is key is that in the monsoon season, the freshwater edge is pushed up till this point. However, in non-monsoon season, the freshwater edge is a few tenths of a kilometers above that point. There's a large, I would say, a significant difference in the positioning of the freshwater to saline water transition between monsoon and non-monsoon. And that's why my quote that a river doesn't behave the same way between 2 days. So you have to be very careful about that. Now, let's move to the other one. So I'll give you a quick example of water flux calculation. This is one place where we try to do water flux calculation to calculate how much exactly the amount of metal is being transported. And you can see these two two poles which are carrying an electrical wire across the pole. So this is the narrowest part of the river in the entire sampling zone. And we tried to quantify the water flux in the narrowest part of the river because we'll get some of the best velocities. And when we look at the velocities, we get a velocity in a non-monsoon, pre-monsoon season, low tide, we get a velocity of around 0.61 meters per second. Whereas when we go to monsoon, between low tide to high tide, we get a velocity which is around 3.5 times that, around 2.1 meters per second. So the river flow can drastically vary between season to season, and the velocity can be around 4 times higher in monsoon versus in non-monsoon. Another factor which controls the river discharge is the tide, whether you are catching it in a low tide or a high tide, or you are catching it on a full moon or a black moon. Now, whenever the samples are collected, we have to measure them. Our analysis strategy was simple. We did the measure ions using an optical emission spectrometer, ICP-OES. We need the minor ions by an ICP-MS, which is a triple quad by Agilent. So you take an alicot, you dilute it to a fixed sodium value, and then you have your standards at the fixed sodium value. You create calibration curves, and you measure your unknown. Some of the ideas was, in any case, that if you are measuring unknown samples, you have to measure standards. So we measured the NIST 1643F, which is a standard known for, I would say, trace metals in fresh water. What we did, we measured it directly. We doped it in different amounts of sodium chloride to mimic a highly saline solution. And what you can observe that we can measure multiple metals with a precision of plus or minus 5% in different matrices, sodium nitrate, sodium chloride, and seawater matrices, which gives us a lot of confidence in the method that we have adopted for this study. So what I will show you in the next few slides is why is it important to have a robust method to measure metal concentration in water samples. Because any mass spectrometer or OES will give you number, whether those numbers are accurate or not. Numbers can be very precise, but whether they are accurate or not is a different question. So when we took that NIST standard for which the values are very well known and measured it directly, this is the kind of values we got within plus or minus 5%, very well. But once we started doping those, that 1643F standard into a matrix which contained 50 ppm of sodium, whereas the standard didn't, we started observing that some of the transition metal values were of the plus or minus 5% limit. And then once we doped it to a 100 ppm sodium matrix, we observed that most of the transition metal values were off the acceptable limit. So that means that you cannot really measure these samples by simple dilution. You need to have a strategy where the standards and the samples are always in the same exact matrix composition. Not only that, when we looked at the ICP-OES measurements, which is considered to be a very robust instrument, and the matrix usually doesn't have much impact on its values, we observed that in presence or absence of sodium, the potassium calibration varied in its sensitivity. And remember one thing, this is standards run and we are observing the intensity on this axis. If the slopes of these lines are different for a particular matrix, what we will observe that when we measure an unknown, we'll have very different concentrations. So we had to re-evaluate our measuring strategy on an ICP-OES to come up with a strategy which gives us the right value. So overall, we had a very good method. We could reproduce all standards in many different matrices. And these values were reproduced at many different constant dilutions because remember, river water concentration values can change drastically across an estuary. So we should be able to measure them at low dilution, which means higher concentration, and high dilution and lower concentration, and we could get same exact results. Reproducibility is good. So all of the data that I'm going to show you has been vetted, tested, verified. So we know that their quality control is there. Remember, this was the monsoon versus non-monsoon salinity profile. We're going to look at some of the elements. We're going to look at concentration on y-axis and salinity on x-axis. The blue colors are monsoon, the red colors are non-monsoon, and these purple colors are different certified standards which were also measured with these elements. And the dashed line gives you the seawater value, and what we should expect is a mixing between the river water value and the seawater value as a straight line, if the element is behaving in a conservative fashion. Now, what I will do is I will move the salinity axis to logarithmic scale. Why? Because the most of the interesting stuff happens in the low salinity region. And if we keep it in the linear scale, all of these data points will be jumbled up in this little corner. So by moving the salinity in a logarithmic scale, I'm going to expand between 0.1 to 1 salinity. And you will be observing how these elements behave in this salinity range. Strontium behaves perfectly linearly. Magnesium behaves perfectly linearly for both seasons. Potassium behaves perfectly linearly for both seasons. Calcium, however, starts to digress from linear behavior between the two seasons. As you can clearly observe that monsoonal values are slightly higher than the non-monsoonal values, and they're showing up even in log scale. So this is something we are going to focus on and try to understand how much of groundwater discharge is happening into the river during monsoon versus non-monsoon. To zoom in to that figure, we have the calcium dissolved in monsoon. This is what it looks like. But once we look at non-monsoon, what we observe, if the straight line is a mixing line, all the values are above the mixing line. So during the non-monsoon season, we have excess of calcium in the river as predicted by a mixing between the freshwater end member and the saline water or the seawater end member. So how do we reconcile that? So what we did, we calculated the percentage calcium anomaly across different salinity zones. And you can see the monsoon values are all within plus or minus 10%. However, the non-monsoon values are extremely high. Now, we have talked about what can be the sources of these calcium anomalies. We can have fresh groundwater discharge which carries calcium with it. We can have recycled seawater discharge which carries calcium with it. Now remember, if you have recycled seawater discharge, your salinity should go up. So you should not be leading to an anomalous value with respect to salinity. We can have dissolution of these calcium carbonate which is coating the SPM, or we can have dissolution of calcium carbonate in the bed sediment which is already sitting there. So we are going through the process of eliminating what are the improbable sources of calcium to river water, and then we're going to zero on the probable sources of calcium to seawater. Now we're going to look at the data on this axis. This is a graph where we are plotting changes in calcium concentration in fluid, percentage changes, versus changes in carbon isotopic composition of the dissolved inorganic carbon in the fluid phase. If you're moving along the x-axis, you're going towards a positive value, which means your calcium concentration is going up. Moving down the x-axis means calcium concentration is going down. Moving up the y-axis, delta 13C is becoming heavier. Moving down the y-axis, delta 13C is becoming lighter. So I'll give you an example. If I respire organic matter, calcium concentration won't change, but the carbon isotopic composition of dissolved inorganic carbon will become lighter and lighter. If I create organic matter by removing DIC into organic phase, I will remove the lighter isotope into organic matter, which would mean the residual DIC will become isotopically heavier. So any productivity leads to isotopically heavy delta 13C of the DIC. Same with CO2 degassing or respiration. Now, if we take our data and plot it on this axis, we see a very strange result. The two sets of values which fall either on the y-axis or parallel to the y-axis. Remember, if I move up and down the y-axis, I'm either undergoing respiration, where organic matter is being oxidized, or I'm undergoing what we call non-dissolution of calcium carbonate, yet supply of isotopically light carbon. Now, one of the ways of changing calcium concentration of the river water is through oxidation of organic matter, lowering of pH, through dissolution of calcium carbonate. But we observe that none of these anomalies can account for that. Okay. Now, the other possible way that I can change calcium concentration is through desorption of calcium from sediments. And we are going to use barium concentration of the river water to calculate how much desorption of elements is happening from the sediments. Again, barium concentration in dissolved phase against salinity. Blue is monsoon, red is non-monsoon. What we observe that there is a mid-salinity peak in barium concentration in all of the seasons. Now remember, barium is attached to suspended particulate matter. Once the river water with its suspended particulate matter encounters waters of slightly higher salinity, these elements from seawater can replace the barium and release it into the river water. As a result, the river water barium concentration will go up. So desorption of element is a possible source of concentration increase in the river water. Let's see whether that works. So this is the SPM maxima. We have already seen this graph, the amount of suspended particulate matter in the river across the 2 seasons. Given what is the barium concentration in the suspended particulate matter, in the exchangeable fraction of the suspended particulate matter, could we account for this excess barium? Then it should also account for the excess calcium. But the barium anomaly that we observe in the river has no correlation with the amount of suspended matter present in the river. And from that perspective, if we have the barium anomaly, this is the mixing line, this is the elevated concentration. And if we look at the barium to aluminium ratio in the weight percentage, what we observe that in the lower salinity region, we have extremely high barium to aluminium ratios. But this exchange of barium cannot account for it. Can we account for the excess barium to groundwater discharge? Yes, we can. The barium contribution due to groundwater distribution is high, but desorption cannot account for it. And we have shown the desorption values for very different values, and it doesn't make sense. So what we will do is move away from ion exchange, focus on to groundwater values. Now, calculating groundwater discharge into a river is tricky. We need to use at least one end member which does not suffer through any of these groundwater discharge or ion exchange processes, which is going to be our sodium. So sodium is kind of invariant to all these different processes. It's only a source-dependent process. There can be no ion exchange. We're going to use barium because it's going to give us an idea of how much groundwater is being pumped into the system. Because why? Because the ion exchange process of barium is not enough to account for the observed changes. And using these 2 parameters, we are going to calculate how much calcium is added by groundwater. And this is what we come up with. Fractional contribution over different salinity range. At low salinity, fractional contribution is dominated by river. There is very little seawater. Seawater is increasing as salinity increases. River water is decreasing as salinity is increasing. And groundwater, we have a maxima at around mid-salinity range, which is quite fascinating to observe. And we calculate that the annual groundwater flux to the Hooghly Estuary, from the Hooghly Estuary to the Bay of Bengal, is around 250 kilometer cube per year. Remember, the water flux was around 1,000 kilometer cube per year. So this is around 25% of the total river water flux. And can it account for the calcium anomaly? Yes, it can. When we look at calcium concentration in the pore waters that we collected, what we observe that the shallow pore waters have excess of calcium. We think that this is dissolution of calcium carbonate through oxidation of organic matter. And this dissolution of calcium carbonate in the pore waters is supplying excess calcium to the river water and giving us the profiles that we get. so forth and so on. We don't need a lot of calcium carbonate, but this works fine. Now, before I end, I'm going to give you a short summary of how these other metals behave in this estuary. I'm going to start with something very drastic, uranium. You don't want a lot of uranium in your water because it's radioactive, and mostly uranium-238. But what we observe that between monsoon and non-monsoon, there's a completely different profile of uranium in the Ganga River. This we expect to be significantly higher because of the groundwater discharge, and usually groundwaters are enriched in uranium. Now, if we move from uranium to manganese, we don't observe something similar. Manganese is giving us a very strange kind of behavior with oxyhydroxide precipitation in the mid-salinity region, sometimes dissolution. And poor water uranium manganese can kind of explain the groundwater dependent concentration profiles. Vanadium, another transition metal, shows a very non-conservative behavior. Remember, this is seawater and this is fresh water. They should follow a line like this. We have this mid-salinity maxima followed by a crash. And where are these elements coming from? When we look at vanadium in the different phases of the sediment, we observe that there's a lot of vanadium locked up in the oxyhydroxide phase. And that's what we expected, right? When the materials being transported are precipitated, like iron, manganese, oxyhydroxide, these are transition metals, and other transitions metals will be co-hosted in that oxyhydroxide. And that's exactly what we observe. That there's a lot of exchangeable or redox sensitive transition metals present in these SPM material which is being transported. Copper, we don't see a similar profile like the with the line. We see a very vanadium-like profile where there's a mid-salinity maxima followed by a crash after that. Similarly, you can see the copper is hosted in the oxyhydroxide phase, and as expected, when the redox state changes, copper is released from the system. This is what the copper map looks like. So we don't know whether this was a compromised data because of sampling artifact or analytical artifact, but our values are very different from the existing published values. And so forth and so on. I'm not going to dwell on this much, but chromium shows a very interesting non-mixing characteristic. So essentially what I'm trying to tell you is that if you took a concentration value from here and took a water flux of the river and multiplied it, you will not get the right answer in terms of a metal flux to the ocean. You have to take these maximas which are happening in the river and take them as the net metal concentration in the river while calculating the metal flux from the river to the ocean. And we know that some of the chromium is being hosted in iron particulate phase, and it is an extremely good correlation between the particulate iron as well as the chromium concentration. Molybdenum shows a very strange profile between monsoon and non-monsoon. This is really interesting. We think it's also redox sensitive. Overall, we have recalculated the amount of vanadium, copper being supplied to the Bay of Bengal by this river. And we think there is almost 16% of the global flux of vanadium is supplied by Ganga Brahmaputra, whereas about 4% of copper is supplied by Ganga Brahmaputra. I'll leave you with that, and I'm happy to take any questions that you have.
Thank you, sir. Thank you, sir. Thank you very much for the interesting
Thank you,
lecture.
Adrian. Yes.
We'll wait for some time if there are any questions.
I think I've confused everyone. Nobody's asking a question.
Usually they type in the chat. Let's wait for a few more minutes.
Okay, let's break them. Nobody has a question.
Okay. There is one question.
Preeti, to answer your question, yes. Depends on what sort of river you are studying. And obviously the metal's original sources are the bedrock. But anthropogenic activity can also add a lot of metal to the river. So the geogenic sources are definitely weathering of the rocks or hot springs or what we call groundwater input to the river. Okay, I think no more questions, then I'll disappear.
Okay, sir. Thank you.
Okay, no problem. Thank you.
Thank you. Thank you for joining us.
No problem. Bye.
Bye.